Okay, so we've gone over now just basic graphing, but now we're going to add a few layers here. Specifically, we're going to talk about oblique asymptotes. Those come up in business applications, actually. We're going to talk about replacement time, which is just a definition, a business definition, which will be easy to get to, replacement time. And absolute extrema on a closed interval. A closed interval is basically a restricted domain. Again, we run into that in business. So we'll need to take a look at that. Okay, so let's start with oblique asymptotes. So how do we find, where do we come up with it first? Let's look at this. If I have a cost function that's $1,000 in fixed cost plus $10 for every item. Does everyone agree that's what that would be? $1,000 fixed cost plus $10 for every item. How do I find the average cost?
Just divided by x.
Divide everything by x. So I get 1,000 divided by x plus 10. And actually, let's write it out this way too. I could take the entirety like that and divide by x, or I could divide each piece by x. It works out to be the same thing. So when I'm looking to graph, let's look at this. Let's look at the function this way. If I'm looking to graph this, I need to, oh, this is a bad example. I'm going to make that a 10x squared. We need to do that. Otherwise, it's too simple an example. So as everyone see what I did? 1,000 plus 10x squared. For some reason, it pertains to an x squared instead of an x. So here I just divide the whole thing by x. If I split it apart, I still get 1,000 over x. And then 10x squared over x becomes 10x. This, right, does not cancel by itself. Right? We can split apart the numerator, but we can't just grab off random pieces to cancel. Okay, so if I wanted to graph this, this is clearly a rational function, so I need to think about asymptotes. What is my, so I have vertical, horizontal, and oblique. What is the vertical asymptote for this? X is where the denominator is 0, so x equals 0. So we have a vertical asymptote, x equals 0. What about a horizontal asymptote? How do we check for that?
Take the leading term.
Yeah, because what we're doing is, this is actually getting back to our limits. Horizontal asymptote is the limit, as x gets really big, of that function. And so that's why we can use leading terms, right? Because we talked about way back when, remember, we said that as x gets really big, the 1,000's not going to matter. Yes?
Wouldn't it be 10x squared?
Yes, thank you. Can you see that? Okay, so leading terms, 10x squared over x. Go ahead and do the simplification right now before you do anything else. So 10x squared over x simplifies to 10x. So the limit as x approaches infinity of 10x. What will that be? If I plugged in x equals infinity, I'd get infinity. So this thing's going off to infinity. Is that a horizontal asymptote?
No.
No. So if you attempt to find the horizontal asymptote by using the leading terms, you will find that there's no number. So there's no horizontal asymptote. Okay. So that means if there's not a horizontal asymptote, you need to check for oblique asymptotes. So let's talk about how we do that. For business applications, it's really easy because typically for business, the only time we encounter this is in this average situation where we have divided by x. That means my denominator is always really, really simple. So the way, here's your method. I'm going to erase this to have a little more space. So to find the oblique asymptote, if you start with something like this, go ahead and do the division or separate it out. Go ahead and write it this way. So you may start with this. You start with that, write it this way. Now, what happens now if I plug in x going to infinity? So let's look at this again. I'm going to look at it now with a different set of, different perspective. Now I don't want to write the limit. As x gets really big, does this term matter? That's going down to 0, right? So this one Anything with an x in the denominator is going to go towards 0 as x gets really big. That means what's left is your oblique asymptote. So everything that goes to 0, you can drop off, and what's left is your oblique asymptote. Clearly, this is going to infinity as x gets really big. We know that. We already figured that out. This tells us how it's going there, because that matters. Because you can envision something going to infinity this way or that way, and they're very different. And so this tells us, we know we're going to infinity as x gets large. We already established that. This just tells us how we're getting there. And that becomes important when you graph, because you need to know, is this thing going like this, or is it going like this? Those are very different graphs in terms of understanding what's important to you. So, okay, so that's how we find oblique asymptote. You may start this way. You want to actually do the division, separate out the numerator so that you've got some pieces that go to 0, and then whatever's left is the oblique. Yes?
So in an average cost function, the oblique asymptote is just simply the limit of the leading term?
Not just the leading term. So let's do an example.
Yeah, I'm trying to figure out why it's different.
I'll show you, because this is too simple. So I'll show you. Okay, so let's look at a couple of examples. Let's answer that question first. So here's an example. Here is a cost function. So 500 in fixed costs, $2 per item, and then there's some other cost that goes up as x squared. So the first thing we're going to do is we want to find the average cost. So we're going to take the whole thing and divide by x. That's how we find average. So 500 plus 2x plus 0.2x squared, all of that over x. So it's a rational function. So we know we have asymptotes. So first, what is our vertical asymptote? X equals 0. Do we have a horizontal asymptote? Check leading terms. X squared over x. That, as x gets big, that's going to get big, so there's no horizontal. So we have vertical, x equals 0. And do not write VA equals 0. Go ahead and write the equation, x equals 0. Horizontal, if we look at the limit of the leading terms, we're going to end up with the limit of 0.2x. And that's going to infinity. So no horizontal. You don't have to write out all of that, but just so that you know where we're getting that from. So when we look at just the leading terms, as x gets really big, the numerator's still getting bigger much faster. So there's no horizontal. So now let's look at oblique. So for oblique, go ahead and separate this out into individual fractions. So we'll have 500 over x plus 2x over x plus 0.2x squared over x. So 500 over x plus 2 plus 0.2x. So again, oblique and horizontal is all about x getting really big. So as x gets really big, what happens to this term?
It gets smaller to
This
0.
one ends up going to 0. As x gets really big, I can ignore that one. Remember, asymptotic behavior is all about what happens way out at the ends. Clearly in the middle, this is going to matter. When x is 1, this matters. When x is 10, this matters. When x is 200,000, maybe not so much, right? So remember, asymptotes are all about big. That's why I can ignore this one. So that means this is my oblique asymptote. So everything that doesn't go to 0, when x gets really big, is what you're left with. So let's go ahead and write an equation. That's an equation of a line. So you need to write it that way. Because again, when you're going to graph it, you need to be, you don't want to just write OA equals that, because that doesn't tell you what to graph. So far, okay? All right, I'm going to leave this one up for a moment, and I'm going to come over here and give you another example. Yes?
So when we're not looking at a business function, right, and we talk about oblique asymptotes, they lose their importance because after a certain number, that 2, which is a constant, doesn't matter much either. But in a business application where it can't be, let's say, more than 500, it's
No,
more important?
no, this adjusts, yes, this describes how it goes to infinity. And so, yes, the 2 seems like it would be fairly
Well,
unimportant.
yeah, isn't it just a shift?
It is a shift, but it is a shift.
Behavior?
But it is a shift, and so that means that the behavior, instead of going like this, goes like that. So it does, so instead of this coming like this, it's gonna come like this. So, yes, by the time we get out to something like 10 billion, no, they're gonna be at about the same place.
Right, I was
But-
just confused because it was a constant and a shift and not a behavior.
Well, but what if this was 20,000?
Right.
Then that, again, it's about the behavior as you're getting there, and so this matters as you're getting there. This matters less. Yes?
So you can never have a horizontal asymptote and an oblique.
Correct. Very good point. You can't have both. Because as x gets to infinity, and so let's look at the next example. As x goes to infinity, either the function is going to infinity or it's going to a constant number. You can't have both. So let's look at this example. I forgot it already. So it's a rational function. So we know that we have to check asymptotes. And I keep repeating things like that because one of the things I don't want you to do is to say, wait, that's like a problem I saw. Don't. And then you go find it and you see if you can make the numbers match. That's my math lab way of doing things, and that's not a really great way. A better way is to understand what kind of problem it is and then know the steps you need to take and the things you need to consider. So because this is a rational function, I need to think about asymptotes. So what are my vertical asymptotes?
-2.
Is wherever the
X
denominator is equal to 0. So this would be x equals -2. Do I have a horizontal asymptote? You always have to ask that first.
How do we know if it's a horizontal? Do we have to
Take
limit
leading,
to infinity or something?
leading terms, and actually, in some ways, this is the same question. The question is, what happens when x gets really big? So look at x going to infinity, and pick off your leading terms. 2x over x. Because as x gets really big, the other smaller pieces don't matter. Go ahead and simplify this. So this would be the limit as x approaches infinity of 2. So the limit of 2 is 2. So I got a concrete number. So what does that tell you? Horizontal asymptote. So I'm going to write that. How do I write that?
Y
Y equals, exactly, y equals 2. So if you do the limit, and it goes off to infinity, you know you have an oblique. If you do the limit and you get a concrete number, you know you have horizontal. So the initial question is the same. What happens when x gets really big? Okay. All right, so let's look at, we're ready to define something called replacement time. So let's look at that.
Shouldn't we find the oblique asymptote or something?
There isn't one because there's a horizontal. You can't have both.
Oh.
Okay, so let's define replacement time. I want to leave this up here because it's a similar. All right, so we are at replacement time. Okay, so replacement time is a very easy definition. It is where the average cost is minimum. So replacement time so that's pretty easy to do. So this cost function actually comes from page 291, number 86, if anyone wants to look at the word problem. So if I want to determine the, okay, I can read it. Okay, so it says the total cost in dollars of producing X city bikes is given by this. So sketch the graphs of the average cost function and the marginal cost function, include oblique asymptotes, and find the minimum average cost. For your assignment, I've said that you can do the graphing using Desmos or your calculator, that's fine. But everyone's yawning. Why is it harder today than Monday? I don't know. Okay, so so there are a couple of things we need to find. We would, in this problem, it asks to graph, we're not going to do all this, graph the average cost function. Which one would that be? This one, yes, the one with the line over it. And so we already know that we already determined that this has an oblique asymptote, right? We already did that work. So let's actually look at that. We know that it's got an oblique asymptote that looks, I should really dot that in, something like that. And we knew it had a vertical asymptote. We already knew that too. So really, this function is going to look something like this. All right? Yes. So if I want to know where it's minimum, I expect that to be right about there. Okay? And we're not going to do it from the graph. We're actually going to do it algebraically. But this is about what the graph looks like. And you can do that from Desmos. We're not going to go through. But I mean, you could do all the graphing techniques that we've used. You could use. But as soon as you have an oblique asymptote, you have to put that on just like horizontal ones. Okay, so that's not. I didn't do that before, did I? So we could graph the average one, which would just be. Oh, that's right. So where replacement time is where this is minimum. So how do I find that? What does that mean? Let's talk about words. If I want to know where, what does that tell me? What answer am I looking for? X. Where is always an X answer? C bar, average cost. I know what function I'm dealing with. Is minimum. What does that tell you need to do? How do you find minimums?
Sign chart.
Sign chart on the first derivative. Anytime you see increasing, decreasing, rate of change, maximum, minimum, extremum, any of those suggest that you need to know about the goings up and down of the function. So this tells you that you have to do the derivative. The derivative of what? The average function. So you start with the average function and then do the derivative. Okay? Do we want to do that one, or do you guys feel comfortable? We should do that. So let's see. I'm going to take this off. And I prefer this one. If I'm do you want to do quotient rule? Do you want to do no? Right, thank you. No, we don't want to do quotient rule. How can we avoid doing quotient rule here?
Simplify.
Just separate it out. We've actually already
500 into a negative exponent.
right. So much easier, right? We agree this is so much easier to do a derivative on because these are really all basics. What do I as soon as I rewrite this? So 500 x to the minus 1. Now everything's a basic. Okay, so let's look. So 500 x to the minus 1 would be negative 500
X to the minus 2.
Derivative of 2 is? Derivative of 0.2 is? 0.2x? So this is actually a good place to review too, because in order to find a min, I need to do a sign chart. In order to do a sign chart, I need to find out where my partition points are. So I need to show you the way this must be done. So this is really this, negative 500 over x squared plus 0.2. You cannot just set this equal to 0, put something on the other side, cross multiply. You lose one of your important partition points. So that anytime you've got this, what you must do first is get one rational function all together. So we need to combine these. So this is really like over 1. So if you're combining fractions, we're just looking for common denominators, which would be what? X squared. So I'm going to end up with negative 500 plus 0.2 x squared all over x squared. Now I can find all my partition points. I'm going to get some from the numerator and 0 from the denominator. And that, for business functions, it's a little less important because we tend to have restricted domains, but in a regular function, we can't lose that 0, which is what happens if you just kind of cross multiply stuff. You end up losing the 0. So here, I'm going to factor out a 0.2. Okay, so from the numerator, now let's go ahead and finish factoring. How will that numerator factor then? We see that's a difference of squares. 2,500 is what squared? 25 is 5 squared, and 100 is 10 squared, so altogether 50 squared. So this would be 0.2 x minus 50, x plus 50, all over x squared. I like it in factors because for me, it's so much easier to do a sign chart in factors. I know a lot of other people don't like to do that. If you want to actually every time find a concrete value, that's fine, you can do that. It's just a little more work. So if you can get to the point where you can concentrate on the signs, you'll go faster. Okay, so what points do I have on my graph then? What are my partition points? 50, negative 50, and 0. So now, this is a business function. Can x ever be negative?
No.
No. So when I start my sign chart, don't even show the part that it does not exist. And if there's an endpoint, if for cost functions there's not, but if there, say for revenue is an endpoint, go ahead and put that on there. So that means my negative 50 I don't need to worry about. That's not going to go on the chart, but 50 will. Okay, so let's pick a number. Any number in there will do. So I want to pick 1. I'm good with 1. And any number over here, 51. Because I'm not actually computing, I don't care so much. So this is always positive. If it were negative, I'd have to include it, as I'm keeping track of signs, but I don't care. So if I put in 1 here, I'll get negative 49, so that's negative. Put 1 here, I get positive. And I put 1 here, positive. So instead of keeping track of them, you can actually write them, and I write them in the visual order I see them. So 1 negative and 2 positives, negative. If I put in 51, I'll get positive, positive, positive. So everything's positive. So what does this mean the function's doing? It's going down, and then it's going up. That's what the first derivative tells us, the ups and downs. So what do I have right here? Min. So where is the min? X equals 50 bikes. That's my replacement. It's a bad example. Replacement time, that's a bad example of replacement time. That's how you find the minimum of a cost function. Yeah, so that's how you would find replacement time, but replacement time doesn't really make so much sense in this example. This was not a good example of that. I'll have to fix that. Okay, so that is replacement time, finding, so importantly, the derivative of the average function means that you find the average function first and then do the derivative. And also, if you ever get something like this, once you've got anything in the denominator, you need to get one big fraction in the denominator and then go from there. Okay, the last thing we need to look at then is absolute extrema on a closed interval. So let's talk about that. In fact, let's just kind of piggyback off of this example. Let's say for some reason you can only make, let's say you can make in this case between 1 and 1,000, 100, 1 and 100 bikes. That's really, you can either make, obviously you have to make some, so you can make 1, but let's say you max out at 100. That's the most you can make. So you might ask, where is your maximum, absolute maximum average cost? So let's think about this. Let's bring it out here a little bit cleaner. So we have 0 to 100 and 50. We know it comes down, but I want to know let's say I really only start at 1. I want to know my max. So I know it's coming down and going up. If I want to know the absolute max, where will that be?
50 and 100.
It will be, well, here it's a min. So it's either going to be a 1, or it's going to be a, do you know which?
No.
Until you plug in numbers, do you know which? No. So when we're talking about absolute extrema, there are some choices. So let me draw you a few graphs. Let's remember, does this have any absolute extrema at all?
No.
No, because it goes to plus and minus infinity, and those are not concrete
I
numbers.
mean, assuming those are arrows.
Yes, we're assuming they're arrows. But let's say that they're not. Now does it have an absolute max and min?
Yes.
Well, yeah. And where would it be? In this case, it's either got to be at an endpoint or it has to be at one of the local max and mins, right? So altogether, when we take this together, what it tells us is that endpoints we have to check and local max and mins we have to check. Okay, so here's our rule. So if we're finding absolute extrema on a closed interval, all right, so to do that, we check endpoints and critical points. Biggest number is the max, smallest number is the min. Did I say sign chart? Did I say those words? I did not. I don't really need to know because the max or min might be at an endpoint. I don't really need to know which of these critical points is a max or min. I just need to find a value because I've got to compare it to the endpoints. So I don't really, there's no sign chart. No sign chart here. All right, so let's do an example. Does that make sense what I'm saying? I mean, it's got, there are really only a limited number of places it could be, so just test all those places, and whichever it gives you the biggest value is the max, and the smallest number is the min. Okay, so let's look at this example. The only other thing that's important is that this has to be a continuous function, right? If you think about all the things that I drew, they were all continuous. If you had a big jump, like an asymptote in the middle, clearly this doesn't work anymore, so it has to be continuous. Okay, so here's an example. Okay, so do I have my endpoints? I already have those. X is 0, x is 10. So before I can go any further, I need to find my critical points. That means I need to do the first derivative, set it equal to 0. So first derivative is easy, 2x minus 2. So what critical point do I get from that? 1. So when I set this equal to 0, I get x equals 1. So that means you're going to set up a list. You're going to set up x equals 1, all your critical values, and then all your endpoints, or vice versa. This doesn't matter. And now you're going to find the y values and see which one's biggest and which one's smallest. So where do you get y values from?
Wait, x equals 10. This, oh, there wasn't a coordinate.
No, this is not a coordinate, right? This is a bracket, so not a coordinate. That's so yeah. So where do I get y values from? From the first one. First one. All right. So if I put in x equals 1, I get 1 minus 2 plus 3. 1 equals 2. If I put in 0, 1 equals 3. Put in 10, 103 minus 20, 83. Does that seem right? Check my math. It's early for me too. All right, so which one's the min and which one's the max? This one, smallest value, absolute min. And this one, biggest value, absolute max. Importantly, this only works if you have a closed interval. If you don't, you can't know until you graph it. So this only works because we have limited the scope. Otherwise, you have to graph the entire thing and look over across the entire thing. Okay.
Wait, where did you get that x equals 10?
That was part of the given problem. I have this function on this
Other
closed.
than 2 x's?
This is a closed interval. It says from x equals 0 to x equals 10. That's what I'm interested in.
Oh.
Yes.
I mean, but couldn't you just, I mean, let's say it was closed from the negative aspect, right? But open the other way. I mean, couldn't you just easily know by looking at the leading term that it's going to go to infinity and then not have to graph it and just say that the min
Yes, but
is x
yes.
equals 1 and y equals 2? You
Yes,
wouldn't have
so-
to graph it to do that.
right. If you knew exactly what it looks like, correct. So if you can tell me exactly what it looks like, good.
Okay. Well, I mean, if you know
Yes.
that it's going off the positive
Yes,
infinity,
right.
you know
But
what
the
I'm
thing
saying,
is,
by
the
looking at
thing
the
is that
leading
we do
term.
this on a closed interval. So
Right.
we got to know the end. There is no open.
Right.
Okay. All right. So